Morning Scholars. Today in quarantine, we're going to be finishing up our Unit 7. Unit 7 encompasses ideas around similar triangles, right triangles, things like the geometric mean theory, our boomerang idea, our content associated with the heartbeat method, and in addition to that, Pythagorean theorem, or a squared plus b squared equals c squared. We're also going to be talking about some of our special triangles, like our 30, 60, 90 right degree triangle and our 45, 45, 90 isosceles right triangle. As you finish up today's lesson, I'm going to mention it throughout, but make sure that you check on Jupyter. We have a Junopod for today's assignment. It's a few multiple choice questions covering some of the ones from the worksheet we do not go over specifically together, but of course I provide context for all of those questions. Lastly, today is Thursday. If you have any types of questions for me, myself, or any of our other teachers, please make sure to hop onto Zoom and check out our office hours. I'd be more than happy to help answer any information with you. Um, Lastly, as well, if you have any questions about anything else, you need some book recommendations, anything like that, please feel free to hit me up. I'll be more than happy to help you out. All right, well, let's get started. All right, scholars, so for this activity, we're just going to be doing in a sense, a review of our most recent chapter, chapter 7. For us to kind of calculate your understanding and all that, what I'd like for you to do is after this video finishes, is to enter into Jupyter, and in Jupyter we'll have a class assignment called Unit 7 Review, or something along those lines, where you'll be able to answer a few questions in regards to a Junopod, and finish up for the day. So not too much stuff. In terms of reviewing the content, what I like for us to start is with our geometric mean theory. If you remember, in the back we had two different concepts we used. We used a boomerang and a heartbeat pattern. And these two concepts allowed us to compare the three triangles that exist within our figure at hand. As we see, like we have our large exterior triangle, we have this little tiny triangle on the left, and then the medium-sized triangle on the right. Our boomerang and our heartbeat pattern allowed us to compare the similar sides without having to actually redraw the figures and pull them out and rotate them around. Our boomerang pattern was when we went from our longest side, came around to our medium side of our exterior figure, and then went from our longest side, stopping the center here, at our medium side. The way that we expressed this as a fraction or a comparative statement was AC, the whole length, and we follow our blue line, wrapping around to segment CB, and that was equivalent to CB or BC over CD. Since these two figures are proportional, we can, in a sense, state that these two fractions are going to be equivalent to one another. The second example was our heartbeat pattern. Our heartbeat pattern went through the middle of our figure, just like a heartbeat does. Heartbeat pattern was AD over DB and BD over BC. So that's AD over DB. We come down BD over DC. And just as a reminder, that when we are considering the notation for our segments, that either one is going to be perfectly fine. DB is equivalent to BD, and AD would be equivalent to DA. The last one that we have is our boomerang pattern. Essentially, we're just going to go the opposite way around our figure. So I'm going to grab another set of, I can't. Come here, kitty. Little cutie. Come over here. Our second boomerang pattern, if we slide down here, we're basically just going to do the same thing but going around and grabbing the values of the smaller side. To do this, I'm going to grab another set of colored markers and we're going to start from the bottom. We're going to go from C all the way around to A and finish up at B. Next thing we're going to do is grab another color marker and we're going to go from BA to AD. We set this up as a statement. I'm going to go from C to A and from A to B. We then go from B to A and from A to D. And just as a reminder, the reason why we're doing this is because we're comparing these different triangles that are inside the figure, but they're related to one another or they're similar, so there's proportionality. That's why we can set up these equivalence statements that we see on the right here. All right, so go to your next page. All right, so now we're going to apply these concepts associated with actual variables or an actual diagram with missing pieces. The first thing that we need to do before we decide boomerang or heartbeat in terms of applying it is to see which variables we do have. So when we go to fill out an equivalency statement, we're not going to be having or not have two unknown variables. So if I'm looking through my graph right now, if I'm going to do something like, for instance, like the heartbeat method, and I go x over z and z over y, I don't really have too much information. However, if I'm going to do something like the boomerang method, I'm going to be able to kind of solve potentially for one of these variables. If I go to the boomerang method to the left and I do 20 over w and then w over x, I'm left with two variables or two unknowns, so I can't really solve for w and x in the same exact equation. But one thing that I am able to do is if I go 20 over 8 and 8 over y, I'll be able to solve for just plain old y. So the way that I wrote this out myself is using my little markers here. I did 20 over 8 and I came back around and I did 8 over y. So to solve for y, I'm going to use the boomerang method. And in terms of showing my work, I'm going to have 20 over 8 equal to 8 over y. From here, I essentially just start to do my algebra. I cross multiply. I have 20y is equal to 64. Divide out my 20 on both sides, and I get a final value of y is equal to 3.2. Cool. So, my next figure. If we're going to solve for x, how are we going to solve for x? All right, so to use x, we actually don't have to use the boomerang method or our heartbeat method. In this case, x is just going to be a portion of this 20 down here in the bottom. And since we've already solved for y, we can just subtract y from 20 and have our remainder of x. The term that we've used in our class thus far in terms of solving for x would be something along the lines of our segment sum postulate. And postulate, if you remember, was that fancy word for our theory or our hypothesis. The segment sum postulate is that the pieces that make up a segment, their sum equals the equivalence of the whole segment. And that we can say like 20 is equal to y plus x. if we just fill in our values, 20 is equal to 3.2 plus x, subtract 3.2 from both sides, and we get a final value of 16.8 for x. All right, so in this question here, we're only asked to find left for z. If we did want to look, for w, we can just do our boomerang going around the opposite side, doing 20 over w, w over 16.8. But if we're going to look for z now, we're going to use our heartbeat method. I'm going to do our fancy z of z. So for z, we're going to use a heartbeat. And we're going to set up with a marker here to help you out. We're going to do x over z, and then z over y. X over z equal to z over y, which is the same thing as just writing it down as 16.8 over z is equal to z over 3.2. Cool. So from here, we're just going to go ahead and do our algebra. We're going to cross multiply 16.8 times 3.2. Show you on the calculator here. Should get 53.76. But if we're going to do 16.8 times 3, clear everything out, 16.8 times 3.2, we get 53.76. 53.76 is equal to z times z, or z squared. To get the value of z, we'll say that's the square root of 53.76. If we enter in 53.76 into our calculator, we end up getting a final value of 7 point bunch of decimals. In this particular case, we can leave it just as such. So remember, in the future for like your Regents exams, things like that, they might ask you if you have, they'll ask you for your answer in a specific way, whether that be something like leave it as a squared in the square root, or find the most accurate answer that's going to be with your decimal points and using the square root in your calculator, or if they leave it as as within most common denominator, then we're looking to break down our radical. So there'll be specificity, but in the case of this, we just are looking for whatever is being asked of us. All right. So what you're going to be doing is in your Jupyter assignment, you're going to be solving for either 1 or 2. I'm going to ask you for variables, and then you're just going to input the values for them. So remember, you can use your heartbeat method, you can use your boomerang. Like for instance, in number 1, if you wanted to find the value of z, you would do 4 plus 9, or 13, over z over 9. Just remember to always stop in the center. All right, so in our next portion here, we're talking about the Pythagorean Theorem and its converse. If we remember back, our Pythagorean Theorem is going to be a squared plus b squared equals c squared. The notion of converse, or its opposite, is meaning like if we're going to be solving for b or a versus just c. So what I'm going to do is question number 1, and in your Jupyter assignment, you're going to be answering one of these 3 questions here. All right, so in number 1, the way that we go about setting up our equation, once again, a squared plus b squared equals c squared. Our C value is going to be the one that's opposite our 90-degree angle, or what you'd call your hypotenuse. Whenever you have a 90-degree angle in a figure, that opposite side is going to be the longest, and that's going to be your C. 13 squared is equal to A or B. We can apply to either of these. Since we're adding, it's reductive. But normally A is going to be your shortest side. B will be your medium side. All right, so next thing we're going to do here is basically just drill down. 13 squared is going to be 169. 12 squared is 144. And x squared we leave as x squared. Minus 144 minus 144, and we get 25 is equal to x squared. So question for you is going to be, what's the square root of 25? That's going to be 5. All right, so in this figure, we end up getting a value of x for 5, and 25 plus 144 equals 169. We also know that, therefore, that is a right triangle. Because if we have another question down on the bottom, write an explanation for you. Here we're being asked on whether or not either of these triangles are a right triangle. So we're going to take a look at number 10. And we're going to be figuring out whether or not these are a right triangle. Essentially what we're looking for is whether or not our Pythagorean theorem actually is true. Oftentimes the way that you might see this question written, a squared plus b squared equals question mark c squared. So in my little figure here, I drew right angle. This is obviously going to be our right angle side. But we're going to set up our equation as 10 squared plus, we're going to put this in parentheses, 2 radical 39. We're going to close our parentheses again. I'll show you why in a second. But squared equal to would essentially be 16 squared. All right, so 16 squared is going to be 256. 10 squared is 100. And to square root this value in terms of just calculating it out, the square root is going to be for the entire equation. So that's going to be for the 2 we're going to square. We can say 2 squared times radical 39 squared. Radical 39 squared is just plain old radical 39. 2 squared is going to be 4. So now we just need to do our last step here. 4 times 39 is going to be 156. Plus 100 equals 256. All right, so does it look like we have a right triangle? So if we add 100 and 156, we get 256. And does 256 equal 256? Yes, we do have a right triangle. So main idea here, whether or not we do have a right triangle, is whether or not we can actually prove the Pythagorean theorem. Like, so for instance, if this value of 16 was, 200 squared or something ridiculous like that, obviously the left side of the equation is not going to equal the right side of the equation, and we wouldn't have a right triangle. So what I want you to do right now, or later on, complete question number 9 here on the left, and that's going to be one of your questions for Jupiter. Okay, so let's look at question number 15 here. We're being asked if whether or not the triangle we're looking at is going to be acute, right, or obtuse. Essentially what we're going to be doing is calculating out our sides and seeing whether or not they're equivalent, as in a right triangle, as in our previous question in our video, or they're acute or obtuse. If it's acute, a squared plus b squared is going to be greater than c squared. If it's obtuse, a squared plus b squared is going to be less than c squared. There's a couple ways that we can do this visually in terms of guessing. Obviously, we can look at the figure and see if it appears like a right triangle, but obviously if we're looking at number 16, this is not 9.6 inches or 18 inches. It's just arbitrarily assigned. So that's why we're going to be able to use formulas to kind of dictate whether or not the numbers provided or have validity. Another thing that we can do kind of just off the bat as well, when we're considering which side to label these, A, B, or C, my question for you would be, which side do we always label C? Like for instance, question 15, which side is going to be C? All right, C is going to be our longest side. So one of the things that we can do to set up this equation here is our C is always going to be opposite our largest angle. We can say that 9 squared plus 12 squared is equal to 17 squared. C being the opposite side, the opposite the largest angle, or the side with the largest length. So just in question number 16, 20.1 would be our C squared because it's the longest side. But 9 squared is 81, 12 squared is 144, and our question here is whether or not it's equal, greater than or less than 289. So if we go ahead and start to combine these values out, 81 plus 144 gives us 225. And is that equal to 289? Obviously not. 225 is going to be less than 289. So what type of triangle is that going to be? All right, so for this one, we're going to get obtuse. So what I want you to do, in Jupyter, you're going to be asked question number 16 to figure out which one of these is running. Just as a reminder, when you're going through your Jupyter assignment, feel free to play this video in another tab as well. All right, so in our next question here, we're going to be looking at this one here on the left. We have a special right triangle, a 45, 45, 90 degree right triangle. Considering we have two congruent angles, that also means we have two congruent sides, or what we would call an isosceles right triangle. One of the cool things about isosceles right triangle is that we have a methodology that we can use to find consistency in the sides. In that, our hypotenuse is always going to be twice as long as each one of our legs. And in theory, we can say in this example down here in the bottom that GT is X and that RT would be X times radical 2 in length. Reflexively, we can also say that RT divided by radical 2 is equal to GT. All we have to do in these examples here is just remember our specific rules in terms of how these guys are structured. What you're going to be doing in Jupyter, one of your questions is going to be answering this little guy right here. To help you out with this first one, with triangle RGT, if our hypotenuse, aka the side opposite our largest angle, is 10 radical 2, and we know for a fact that we have an isosceles triangle because we have two congruent sides, dictated by the notation, that if we want to find side GT, we would divide by radical 2, and 10 radical 2 divided by radical 2 is just plain old 10. When you're answering this question, remember your opposite side is going to be your hypotenuse, and your hypotenuse is going to be radical 2 times longer than your legs. If we look down here in the bottom, we also have another figure in a similar fashion. This particular triangle is going to be another form of special right triangle. It's set up as a 30, 60, 90. Such that, for instance, in this triangle here on the right, we know we have 90 and 30. If we want to find this last angle, we would do 180 minus 90 minus 30, which is 60. In terms of our rules, they're slightly different with these particular type of figures. If we look down here on the bottom, this nice little diagram I got drawn out for you, our smallest side is going to be opposite our 30-degree angle, and we label that typically as x. Our medium side, still connected to the 90-degree angle, is going to be radical 3 times longer than our smallest side. And our hypotenuse, the side opposite our 90-degree angle, is going to be our 2x side. For instance, in this figure over here, 30 is going to be x. Our side opposite of 60 is our radical 3 side, our x radical 3. Our hypotenuse is going to be our 2x side. What I'd like for you to do in this equation here is find the value of x.